Yes, so my name is Rayssa, and I will talk with you today about probing biological samples with quantum light. And I would like to say first, right, thank you for the organizers for inviting me for this presentation. I think it's really an honor to speak in the Quantum Science Days that are organized by QWorld. A bit about me, I'm an optical engineer at Indicative Photonics. It's a Danish company, and I work in the quantum solutions team, developing fiber laser solutions to be used in the quantum computer and sensing fields. So this is my daily job, and in my free time, I collaborate with some organizations. One of them is High Five Girls, that is a Danish organization that bring young girls from the age of 13 to 19 years old in close contact with the field of STEM. And you do it by promoting camps and hackathons with women role models that work like in robotics, computer science, physics, math, quantum technologies, and more. And also as part of my activities, I'm part of the Humanium Foundation, and I'm leading the hardware team for the Humanium Quantum Program. I will talk more about it later in this talk, but in our last year's program, we trained more than 1,000 participants for more than 70 countries during 7 weeks. And in the end of my presentation, I also invite you to join this year's edition. So the talk that I will show to you today, it's about the work that I did when I was a researcher at DTU, that is the Technical University of Denmark, and I was working in the Quantum Physics Information and Technology group. Okay, so let's start. What is the outline of this presentation? We'll talk, I will present to you some quantum sense experiments using squeezed states of light. We will dive in a bit on the quantum optics domain, and I will show you some experimental results using the squeezing states of light to probe different kind of samples, especially biological samples. So let's start a bit, I like to say a bit of history here. I think it's really nice to show how things started. So when you go like back in time, around the 80s, we had already a certain number of papers talking about the theoretical side of squeezed states of light. And I really like this talk that was given by Levison in the summer of '85, where in which he mentions from experimentalist points of view, squeezed states research can be best described as a series of difficulties that must somehow be overcome. And I would say that this is valid in general, not just for squeezed states of light, but until that moment, it was still not possible to measure squeezing. And when you go just a bit further in time, like in the fall of '85, we have the first signature of squeezed light being measured in slush labs, and this was around 0.3 dB of squeezing. We can see here in this picture on the A side here. And after this first measurement in the fall of '85, we had several groups. It was a race for who could measure squeezing first and who would measure more. And by the around like summer '86, we already have measured like 3.5 dB of squeezing in this short period of time. So, and today, when you see today, like state-of-the-art setups using light, we can measure around 15 dBs of squeezing. And what are squeezing, right? I'm talking to you that we did it, but what are these states? What are squeezed states of light? So using very simple words, a quantum state is called a squeezed state if the variance of one of the field quadratures is below the variance of a vacuum or a coherent state. What does it mean? It means like if you imagine like that you have a perfect laser system, right? You remove all the technical noise present in your laser. If you do a measurement of this light, you will still see some fluctuations present in the noise that comes from the laser. So you cannot go below it unless you use another class of quantum states of light. and the squeezed states present less noise than the noise present in the short noise level of this laser, of the best laser that exists. Okay, so we say that, so this is what translates the sentence, and it needs to obey the Heisenberg's uncertainty, in which you need to fulfill this inequality. The product of the two conjugated quadratures needs to be larger or equal to 1. And so we started, right, detecting squeezing in around the 80s. And also, just to finish our storytelling here, around 81, it was a theoretical proposal by Cave. It's a very famous paper in which he proposed the use of squeezed states of light in the empty entries of an interferometer to increase the signal-to-noise ratio. By that time, we didn't have measured yet these states, but today, this is one of the, like the big example of success of application of this resource is the LIGI gravitational wave detectors, right? In which you have enhanced sensitivity by using squeezed states of light. So most of the experiments that we see in general about squeezed states, they goes in this direction, mostly for phase measurements. But today I would like to talk with you about another kind of measurements that goes in the direction of amplitude measurements. Okay, so what comes next? We have like enhanced sensing experiments, and you cannot see my screen, right? It didn't change. Yes, in which we can measure like biological samples beyond the quantum limit. And when we say it, it's because you are not more measuring in the short noise limit, you are not limited by the short noise of the laser system. You can go beyond it, okay? And you can do measurements, for example, for tracking lipids in yeast cells. This was one measurement in 2013 made in a group in Australia. You can do quantum-enhanced stimulation, for example, detection for label-free microscopy. And label-free means that you are not labeling your sample with any marker, but you can, because the samples have a signature, like a frequency that you can measure, like some vibrational frequency. So you can probe it, and you can see the signature of your sample using this technique here, for example. And when you use squeezed states of light, you are going to have a better signal-to-noise ratio because you decrease the noise flow. Other kind of systems that use it is quantum-enhanced stimulated Raman scattering spectroscopy. And here I show you two experiments, one using continuous wave on the left, that was published in the group that I was working with, in which we take the polymer sample and probe using coherent states of light and squeezed states of light, but to characterize the vibrational modes of the polymer understood here. Soon afterwards, we had the publication of this paper called Quantum-Enhanced linear microscopy, also from an Australian group, in which they use the same technique in a state-of-the-art system using pulsed lasers to probe yeast cells and to measure the vibrational modes there using also coherent states and discrete states of light. And why do you have the interest of doing it? Because biological samples, they can be quite sensitive to the optical power that you use on your sample. And this can cause one effect that is called photodamage. If you have it, we can see here, for example, in this example, we have this scan, this section here, and you can scan it like, for example, 30 times, you see almost no damage. But when you scan more and more, so you are exposing your sample with light for more time, you start to see damage signatures on your sample. And we wouldn't like to do it, right? Here it's a bit more dramatic effect, like you have DNA in an undamaged cell. And when you have a lot of light input on your sample, you start damaging it. And when you use and how can we overcome it? One way is to, instead of increasing the optical power level to increase your signal to noise ratio, is to reduce your noise floor and having a good signal to noise ratio. Okay, so I will show you how we can do it. And just to clarify what I mean by the signal to noise ratio. So here on this video that I'll show you now, you see that when the optical power decreases, the signal to noise ratio decreases until your signal is inside your noise. Okay, if you have squeezed states of light, what will happen is something similar to this video here, in which in purple you have a squeezed state with a signal to noise ratio that's bigger than the one using the coherent light here. And you see that just close to the end, your signal is again inside your noise, but for a long time it was bigger than the noise. Okay? And so this is an introduction about the area. So I will go a bit deeper now in the quantum optics domain, and we'll see some experiments afterwards using this class of states. So, can you see my screen changing, or is it still in the video? Okay.
Now it's changed.
Now it's changed, yes. So when you are in the continuous variable domain, we describe the electromagnetic field, the quantized electromagnetic field, in terms of the field quadratures that is represented by this X quadrature here and the Y quadrature. So these quadrature operators, they are described in terms of the annihilation and creation operators, and they obey a commutation relation that leads to the Heisenberg uncertainty principle. So this is kind of a general overview of how we do with the field quadratures. We represent it in the phase space. That is a space that have the X and Y quadratures. They are orthogonal between each other. And if you have a classical system, like you don't see a dashed area in the phase space, you see a point there, right? Because you can determine with precision where you are. But when you have a quantum system, we have this uncertainty related to your quadratures. So you don't have, you cannot say with infinite precision that you are here or you are there, but you have this uncertainty associated to it. And this is the reason that here, representing a vacuum state, you see a circle with a dashed area in which the noise in each quadrature, like in X and Y, has the same size. And this represents the minimum amount of noise that is present, when you talk, like this is what represents like the short noise limit that I was talking before. And this will be our, let's say, the standard that we're going to use to compare a different class of states with. So when we have, for example, I will show you two classes of quantum states of light. One of them is the coherent states. So we have a vacuum state, and we can displace it. So now when we displace the vacuum state, we have a mean value associated with it that's represented by this arrow, and this is a coherent state. And when you say like your electromagnetic field oscillating, this is a time evolution that's represented here by this circle changing in time. Okay. You also have a class of state that is called squeezed states, and these squeezed states, as I mentioned before, right? They represent less noise in one quadrature. So you see here, comparatively to your vacuum state, you have less noise here. But in the other quadrature, you need to have excess of noise. And you can do it in the amplitude or in the phase, or you can also rotate this ellipse around, and you can have squeezing and anti-squeezing changing, okay, depending on the angle. We need to measure these states, and the way that we do for measuring it is using a photo detection scheme. in which we split between the high frequency part and the low frequency part. The high frequency is called HF, and the low frequency is called the DC. We generally measure the DC in the oscilloscope, and the high frequency go to your spectral analyzer or your acquisition system. So a typical measurement is represented here. You have the electronic noise of your system, so no light is going on, is input in your detector. And you have your lazy noise. And your lazy noise has this typical 1/F signature here that goes to the shock noise in terms of the frequency. We say that we have a main carrier, in this case to represent the light, and we are interested in the noise that's expressed in the sidebands. And we can do two types of measurement. One is the amplitude quadrature measurement, that is the direct detection, in which we have access to the amplitude quadrature here. We do it by taking our intensity operator, that's written in terms of the number operator. We have the annihilation operator in terms of the field quadratures here, and you can split this operator in terms of a mean value plus a fluctuation. We are interested in this fluctuation here. If you would like to measure the phase quadrature, you need to have some interferometric technique, and it can be HOMODYNE detection or noise ellipse detection or rotation, for example. And for generating these states, you need to use, so we are talking about the laser, right, that has a certain noise. So when you would like to generate a squeezed states of light, you need to pass laser light in a nonlinear medium. And in this case here, we're talking about a second order nonlinearity, in which photons of your pump beam will be converted in photons of signal and idler beams. And they obey this relation here, that is this second order Hamiltonian here. You can have it in bulk systems like free space optics or in waveguides and going to the direction of ship size to generate these states. In the experiments that I show you, we use a nonlinear cavity with a nonlinear crystal inside it, that is the Chi2 medium here, in which we pump with certain wavelength, and you generate squeezed vacuum states in the output of this cavity. Okay, so what do you do afterwards? We need to characterize the system, and you do it by using HOMODYNE detection. So the HOMODYNE detection process works by, you have your signal being here that can be your squeezed state, your vacuum state, and you interfere it with a local oscillator that has a certain, you can change the phase of this local oscillator. Part of the signal will come to this direction of the detector, part will come here. You can subtract these two signals, and if here in your signal path you have a vacuum state, you measure the shock noise level. Okay, here it's normalized. If you have a squeezed state come here, and if the phase is aligned for squeezing, you measure this signature here. So here you can see that we have around 6 dB of squeezing that tends to the shock noise here with the frequency in this region. Okay, and here you can measure the anti-squeezing, that's the quadrature, you just need to change the phase, also in terms of the frequency. If you look just to a single frequency, you are not looking the spectrum, but just to one frequency, you can see here what we call kind of McDonald's curves, like change, right? Anti-squeezing, squeezing, anti-squeezing, squeezing, because the phase of the local oscillator is changing here. What will you do? Will take this one frequency here and look in the squeezing part of it, and do a set of experiments using these states. Okay, so now we have we know how to produce these squeezed states of light, we know how to measure it, and now we're going to apply these states. And how do you do it? I'll show you the first experiment that is using stimulated Raman scattering, and it's a vibrational spectroscopy technique that's very powerful for imaging biological samples. So when you are looking into these Raman techniques, you are like each element of the molecule has a different response. And because of it, you can selectively like imaging different signatures of our biological samples. And it's also label free, as I mentioned before. And yeah, you don't have any interference from the species. So let me see here if I can change my slide. Yes, so here so what happens here is, sorry, I'm having a bit of trouble with these slides. Yes. You have your sample, as I mentioned before, and we are going to have two lasers input on this sample, in which you have a pump laser and a Stokes beam. Both of them will probe a vibrational mode of the sample. And when the difference in energy between the pump and the Stokes beam matches a vibrational frequency of your sample, you will have a gain in the Stokes beam and loss in the pump beam. So this happened like here in this virtual diagram. But to measure these losses, the intensity that was lost in the pump beam or the gain that was again in the Stokes beam is very hard because these are very small signatures. So what we do is a technique that we use an amplitude modulation in the pump beam, and you have the Stokes beam, right? So when both beams come to the sample, pass through the sample, we'll have there is an energy conservation happening here. So the amplitude modulation that's present in your pump beam will be transferred to your Stokes beam. And if you are matching the vibrational frequency of interest that we're looking for, we can filter out the pump beam here in this system, and you measure just the Stokes beam that was not modulated. But if you are seeing the signal, you will see a modulation in your Stokes beam here in your acquisition system. And you do it using two different classes of states, like a coherent beam, that's our classical limit here. And when you do it, for example, you have the signature here that's around the frequency that we're modulating the pump beam. But remember, we are measuring the Stokes. This sample is a PMMA, and you are reaching the CH strength modes here, okay? That the signal to microwave is bigger. Sorry. Yeah, it's fine. Okay. This technique is proportional to the optical pump power that inputs in our system, and you see that the signal to noise rate increases using squeezed states of light when you compare with the coherent state. Okay, here just to show that you can also characterize the spectrum of your sample using also both classes of states. So this is one way that we're using polymer samples. And after this work, we published this work in Optica in 2020. It was a collaboration between DTU and DFM. And soon after it, we have several developments in the field, from a state-of-the-art setup to high-power measurements. So sometimes you show that it's possible and things happen, okay? And now how we go beyond, right? Here we are talking about doing measurements of polymer samples. People are trying to do measurements using biosamples and all the kind of different kind of samples. We decided to do an imaging system using this class of states. And in this picture here that you can see on your screen is just to show you how this is an optical table when you are doing this kind of experiments in free space setups. So here is a laser system, very in the beginning. This is a full optical table. And here is the microscope that we are going to use. Our squeezer generator is this small thing here, as you can probably not see very well in the picture, okay? So what are we doing here? We will use coherent and squeezed states of light to probe a sample, and we will see how better is the enhancement of the signal-to-noise ratio when using this squeezed beam. What is the challenge here? We are going to use a proper biological sample. It's a cell, and there are THP1 cells. There are cells from the immune system, and they have like these features here. When you look in a bright field microscope, they are around 25 micrometers. They have a membrane around and a nucleus inside. Okay, so we'll try to image it using this class of states. And when you are going to work with biological samples, you have all the challenges associated with keeping the sample in your system. So how do we start it, right? So we have our coherent beam, or we have a coherent beam here that will be a local oscillator. We'll modulate it, amplitude modulate this local oscillator, and we will interfere it with the probe beam. That can be a coherent state or the vacuum state, or the squeezed state, okay? And you detect. So when we do it, we have several measurements here. So the orange one means the electronic noise of your detector, okay? And the red one here is when you have vacuum come on your system. So you're measuring the shock noise. Now you have added to this system the blue trace that is squeezing. Instead of having vacuum, we have squeezed states of light. And you see that the noise is reduced when compared to the red curve, that is the shock noise. And here, instead of having squeezing, we have anti-squeezing. That is the excess of noise quadrature that we have in our system. And here you can see that you have more noise than the shock noise and the squeezed level, okay? And so this is the representation of the system. And what do? We take your sample and you probe force with coherent light, as you can see here. And you see that the image is a bit disorganized. So when you do it with squeezed light, because you reduce the noise, the error is smaller, and you can see a better organization of your picture. So here you barely can distinguish this feature, and here it's clear that you have something inside and some covering outside, right? So now we're looking in the mean number of photons that are probed in the sample, and you can probe very low number of photons, like from 0 points in average, right? 0.2, 0.3 to 2 to 200, more than 200 photons. And we do it by changing the voltage that you apply in your amplitude modulator. And if you have a certain amplitude there, for example, 50 millivolts peak to peak, you can have a signal-to-noise ratio using coherent light that's around 29 dB. And this is the signature that you have from your cell. And when you have squeezed states of light, you start to differentiate better the components of the cells because you have a better signal-to-noise ratio. And you can do it for several different voltages that you apply in your amplitude modulator until you go very low number of photons here, like 2 millivolts peak to peak, in which you are very noisy in the picture on the left. But even though you are noisy in the picture on the right, you can still see a better organization of the features in your cell, okay? So to like to show this second result to you, that is like when you have a coherent light and squeezed states of light, you are able to image in a biological sample, and even though you're in a region that has a very low number of photons, you can still see better using squeezed states of light than using coherent states of light. This paper is in preparation. And the last experiment that I'd like to show you, it's going the same direction. So the idea is probe using coherent states and the squeezed states, but now we are going to sense the bacterial growth. So we are having bacteria in our setup, and we would like to try to see if you can detect earlier the bacterial growth using quantum states of light, okay? Here, this is a work that's part of the QUADRATURE project. It was a collaboration between, it's a European project, and I was working close contact with Gaetano and Stefano from the University of York, and the group at DTU, like Ulrich and Tobias and I from QUBIT, and Christina and Annie from the Health Tech department at DTU. So what do we have here? What do we want? We want why do we want, right? So bacteria can be very, how do I say, hard to deal with, right? And you'd like a way to detect it earlier in time. So you can see if in your sample you have it or not, because it's very important, especially for food poisoning, like to know as early as possible if you have a bacteria there, right? So these are theoretical results that you can see in the screen, and you are going to the experiment now. So just a bit of fun, right? What we're doing, we're taking quantum physics and putting together with bacteria. And here says that teamwork make the dream work. This is for a completely different thing, but in the end makes sense, because when you are working with bacteria, one needs to learn how to grow this sample and how to deal with the sample, okay? I'm a quantum optics physicist, and I needed to learn a lot, especially with Anna and Christina, how to deal with these small things. So what does bacteria require? It requires like nutrition, a nice pH, temperature, and the oxygen, okay? So you have them from an agar plate, and you grow it what you call overnight culture. So you take it from your culture, and you are starting to do your growth curve. So I will not tell too much about how we do it, but we put this in an incubator, and you measure it normally, usually in a spectrophotometer, and you see that how the bacteria grows over time, okay? You measure the absorbance here. So this is your parameter, the parameter that we are looking for. You have four main phases. That's the lag phase. That's like when you're starting to grow. You have the log exponential phase, that they're growing fast and they are eating very well. They're happy here. You have the stationary phase. You have a equilibrium between, there is a constant growth from this point on. And you have the death phase. That's when you don't have as much food in your environment anymore and the bacteria starts to die, okay? What we are going to do. So in the normal system, you have an incubator that you put your bacteria inside. It will shake, it will keep it warm, you remove a sample, and you put in your spectrophotometer here, and you measure a count. In our system, we have a mini incubator that I'm calling this one here. We have a cuvette inside it. I will leave the bacteria there growing, and they will be measuring constantly over time, okay? So this is what we're going to do in the whole experiment, but instead of using classical spectrophotometer to do the measurement, we will use a class of special states that are the squeezed and the quantum and the coherent states of light. And we would like to see this curve here happening there, okay? So how you do it? Again, same principle. You have your squeezed source. You have your displacement beam, that's your coherent beam that I called in the cell experiment. We are going to interfere both beams together. They are going to pass through our sample, and we are going to acquire them. And here we have a shutter. So what is going to happen? First, we need to measure the blank. The blank is when you don't have bacteria in your medium. It's just the food part, just the medium part. And you do it by measuring squeezing when the shutter is open. So you open the shutter, you have squeezed light, you do the measurement. And you close it, you have a vacuum, so you measure your coherent light measurement. Okay, so you have vacuum come here, you displace it with a coherent beam, and you do the coherent light measurement. Afterwards, we have the sample in the container now. So you do some calculations, put the sample there, and you do the same for a long period of time. Take every minute a measurement of squeezed state and a measure of coherent state of light. And when we do it, we have some nice curves here that shows that. So here is the blank, this first one. So there is no bacteria in your system. And you do the measurement with squeezing, that you see that the error bars are smaller in purple or in red. And with coherent states, that you see that the error bars are larger, okay? When you have the bacteria, we start from a certain point here. So this is your mean value. And you see that this is decreasing with time, right? So, sorry, yes. When time passes here, it decreases because bacteria is growing inside your container. So when light is passing, you have more losses. And for sure, you have a mean value that's smaller than the one that you had in the time before. When this happens, what happens with the squeezing, right, with the noise? The noise tends to what we call the short noise limit, because squeezed states are very fragile in the presence of loss. So here you had the maximum transmission and you had a certain number of squeezing. When the bacteria starts to grow, you see that the transmission changes, you have more losses, and your squeezing also changes. You decrease the amount of squeezing that you have in your system. And this, if I measured for more time, it would go on until you are here in the short noise level. With this data, we can compute the absorbance that we have in our system and the error associated to it. And you have these two pictures, this figure here showing two curves, in blue with coherent states of light and in red with squeezed states. And here we performed a truncation that is called Gaussian truncation for not having an absorbance that's smaller than 0, because it does not make sense. So you truncate your Gaussian in the beginning between 0 and the maximum value that we are measuring, okay? We use a bond parts function. That's the kind of special function for characterizing growth. And as after we do this measurement, we saw that the measurement takes more than 5 hours to be done. We would like to know how early we can detect and how early we can detect using coherent states of squeezed states of light when comparing with squeezed states of light. And for doing so, we have in blue here a coherent state measurement, and in this curve here is the transmission over time, and in constant here is the blank. So we see that we start to differentiate the blank, that's the upper one, from the growth around here, right? So 1.2 hours, something like this. But if you just come here in the squeezed curve right now, you see that you can differentiate the growth from the blank earlier in time than using coherent states of light. So here you can already see the advantage of using these states for probing growth, because you could do a shorter time measurement with squeezed states, and you'd be able to see your sample. You'll be able to detect that you have growth in your sample. And to assure it, we do some probability calculations. That's the mean error probability, when you consider that both the false negative and the false positive has equal costs. And you can see that for the same time, you can have you can detect earlier using squeezing than using coherent states. And the same for the false negative, right? That you measure something, but in reality, you didn't have it. And you can see that for using squeezed states of light, this measurement can be done. You have the probability of having false negatives is smaller earlier with squeezed states than with coherent states. So this is what I would like to talk with you about this problem of biological samples using squeezed states of light. I showed to you 3 different experiments, one using vibrational spectroscopy, another one doing bioimaging, and the other one is another absorbance experiment that is probing the bacterial growth. I would like to say thank you for watching the presentation. And before I open for questions, I would like just to use 2 minutes of your time to talk about the global quantum program that we are doing at the Millennium. I would like to invite all of you to register to this program. We'll have a program run on July in which we'll cover quantum computing, quantum sensing, applications and startups. Like we have virtual lab tools, and also a part of the program that will be the Quantum Solutions Lab that's about solving challenges for the industry and bringing solutions to the new industries. Okay. It's an amazing program that will have more than 70 speakers, and will happen from July, from the 2nd of July to the 28th. And you have, for example, several companies will be present, right? For the quantum computer hardware, we have lab tools at IQN, D-Wave, Quantino. We have for every main quantum computer hardware platform, we have a lecture about it. We have the quantum computing software boot camps, and we invite all of you to join. And also QWorld is our collaborator there, and they will have a quantum algorithms and quantum error correction course. We have quantum sensing and quantum communication and applications as well. So we expect to join more than 1,000 people for 4 weeks with more than seven speakers. And here you can have a sneak of the speakers that will be in our program. And with that, I would like to say thank you to the organizers again, and thank you all for listening. And yes, questions if you have any.
Thank you very much. That was really interesting. I mean, I'm not a quantum optician by any means, but this is really fascinating. How can you actually manipulate with light? And this is, I mean, this is great. First of all, there was one question I think I missed from the chat about the HOMODYNE detection you are using for the for your setup. And the question was, is there any other detection method at HOMODYNE? Why is this the best method?
Oh, sorry. Yeah. So yeah, now can you hear me? Yeah. So HOMODYNE detection we use when you would like to characterize the phase space, right? So you can change the phase of your local oscillator, and you can beat it with your signal, and you can characterize in quantum optics what we call the covariance matrix, part of the covariance matrix. But in reality, what I was using is direct detection. That's easier because you don't need to use 2 photodetectors, and you don't need to do mode matching between the signal beam and the local oscillator beam. In general, we use these interferometric techniques if you'd like to characterize phase. But in my case, I was really interested in the amplitude, just the intensity. So you have literally just one detector in the end, and you characterize the light that comes, and you just measure the intensity quadrature, the amplitude quadrature there. So there are different methods and techniques, and everything depends on what we are trying to measure. Yes, so it depends. In my case, I don't need to choose the proper HOMODYNE setup. I can use just one detector there.
Okay. Any other questions? Does it mean you created a squeezed system and attached them to the instrument?
Yes.
So does it mean you created?
Yeah, it's more or less like this. I like to say that in the future, we would like to have a squeezed system in a box, right? The Raman system in another box, and you put both together. But right now, we build the squeezed setup and the squeezed setup, the squeezed setup and the Raman setup, and we connect them together. But it's possible, yes, to have the squeezed system to imagine, right, having it in a commercial box, let's say, and couple it to your HOMO setup. The only thing that I would like to call attention here is that squeezed state supply, they are very fragile to losses. So all the system that we're going to couple it with needs to be well prepared for having like low losses in the optics, so you don't lose it in your optical path.
Okay, so I understand that this requires extra cautions with actually fabricating this kind of instruments, right? Okay, okay. Okay, so thank you very much. Thanks once again. I have also a question about this womanium. Yeah, I checked the webpage today before the session, and there was actually one question I would also like to ask. Is this only for women? Is this only for girls, this program?
No,
because...
it's for everybody. Everybody can join, and everybody is very welcome. We're expecting all people from all over the world.
So why is this name suggesting that that you are...
The main idea is to have young women contact the front-end technology, so to call attention to it. But all the programs are open to everybody. The name is to call attention, right? Unfortunately, today, we still have a lack of representation in STEM. But with time, we can change it, and we need to put this in the, let's say, the front page, right?
Okay, okay, now I understand. But okay, anyhow, so I encourage you guys to
join the program. It will be an amazing
join really,
program.
and I know that also QWorld is doing a great job in this area of actually making courses on quantum computing. I also participated in some of them. Okay, so thank you once again. It was a very nice and interesting talk.